So today the plan is to discuss about finite element method, and then a little bit about model reduction technique. And what comes to midterm exam, first midterm exam, the subject matter that I'm about to explain today is the most important subject matter. So for sure there will be a question that is related to model reduction, and for sure there is something that is related to safe functions and finite element method subject matters that I'm about to explain you today. Now I have some practical matters to discuss before we are entering the first the summary of the previous lecture and then the new material. And the first practical matter is there is a recruiting meeting event tomorrow. It's almost a full day event, and it starts at 10 o'clock and it ends at 3. So it's going to be here in University Building number 1, and it will be located in a first floor. This is a first floor, second and third. And I would like you to be aware of that, because this is a great opportunity to look at the career opportunities out from the universities. There is a total of more than 100 companies that will be here in the university, and they are hiring. They're hiring people. So highly recommended to take some time and go and walk around to see what is that they can offer for you. And of course, a little later we will discuss about details of kind of like career counseling lecture. But I realized that it would be nice to have this career counseling prior to this career or this recruiting event. But I'm going to be a little late. But what you can do in your side is that you go and be active there, and then later I will explain what is needed in interviews and so on and so forth. All right? So how it sounds. And at least what makes sense is that there's more than 100 companies. They have a booth. Each one of them will have a booth, and they're offering candies. So that's what I will take a full advance. I will go and collect a lot of candies because I like sweet stuff. All right, so so that's tomorrow. Tomorrow starting at 10. You were aware of this prior to this lecture, right? Okay, good. That's good. Okay, then there was a question regarding the midterm exam and enrollment to midterm exam. To be honest, I don't know how it goes, but I suppose that you need to log into website some kind. You need somebody have to help me. So when you enrolling an exam, how is that you can make it happen? You go to, is it uni.lut.fi, or what's a website you can make it happen? Webbody. So you log into Webbody, and in the Webbody you can see all these meetings that are available. So this is where you're enrolling to course itself, right? No. Yes, it's the same thing. Now, when you log into that website, you should be able to see this one here, this code here. Let me try to. This one here, which is our code of the course, and then this famous letter V that stands for midterm exam. This is where you need to do your enrollment, and you need to do that well before the real midterm exam. I don't know what's the time limit, but I believe that the week ahead, or how much it is. You don't know that, or do you? You're not sure about that. I think that it would be because if you know already this time that you will participate the midterm exam, go ahead and do the registration, do the enrollment, because no harm will be done. Because the problem is that if you do it late, then there are two options. Either the Student Affairs Office is not allowing you to register, which is a major drawback for you, or it allows you to do the registration, but you have to pay some penalties. I don't know how many thousand euros is the penalty, but it's, do you know how much it is? Is it like 20 euros or something? But it's a payment some kind that you have to do, which makes no sense, because you can do it in a timely manner too. So again, log into web audit, take a look at the events. Can you see that event already there? And try to look at this one here, which is our course code, and then the letter V. And again, the V stands for this midterm exam. Okay? And then again, you need to do it prior to, well before this exam, because I don't think it is possible day before, 2 days before, but well before. I don't know how much before, because the teachers are not involved in this kind of practicalities that are related to exams. So I don't know that, and I will not be present in that midterm exam. So that's different than in other universities, because in other universities I know that in many cases the professor is there and you can even raise your hand and ask a question if there's something that you don't understand in the questions. So I'm not going to be there. Later, of course, you will have your opportunity to check how was your performance, and you can, if you want, you can set the appointment with me and try to build the case to upgrade your performance from the midterm exam. Okay. So is this clear? So do you know how to do the enrollment, how to register the midterm exam? Is it that you don't see the code? This is how the code reads. Is it clear? Okay, so it's all clear. You sure about that? Okay. And this is the day that the first midterm exam will be organized. Here's the second. And I said that I have no power to change these dates, and that's correct. I have no power to change these dates, but if there is some serious issue, if there is a commitment that you have made and these dates are not fitting to you, so we being flexible in terms of the dates in previous years, meaning that we can organize an exam for you. So it's meaning that there's almost like a private exam event, and some of the students will go and do that exam in a lecture room that we will look that you're not doing any cheating. Okay, so that's how it goes. So, clear. Then, and again, I will organize a date, time of the date that you can come and take a look how was your exam. And I recommend you to take that opportunity. I know that is not common in Finland. Usually it doesn't really matter how well you perform in exam, but you never ever come and check, how are the correct answers and what actually you did wrong. But I recommend you to take this opportunity in this class. And anyone from Spain in this class? No one from Spain. But this was a really long time ago. I worked in the University of Seville, and it was a quite nice experience because one day when I came to my office, there was my supervisor office was next to my office, and there was a lot of people in a corridor. It was really, really packed. And I was like, what is special about this day? And then the professor explained, today is a special day because students will have the opportunity to come and check how is an exam, how was the exam, and how it went. I hear it because the walls were really thin in Spain. I hear that someone went into the professor's office, then they started to discuss like that, and then they started to yell at each other, you really yelling, no, you are not a good professor, you don't know how to teach. And then they were yelling to each other, and then slam, the door was closed again, and the next, and again and again. So that was state policy. So consider to use that, or even better. Once I heard that there was one student that came to see the exam with his mom. And the mom was yelling to the professor and say, you're not a good professor, so if you take your mom or dad with you, I will give you a special treatment. Okay? Consider that. All right. Okay, then another note. We will have a little bit of special schedule on next week. So we will have a visiting lecture. So what will happen is that I will deliver lecture on Monday, but in addition to Monday's lecture, there's another lecture that will be on Thursday. And this may not be the time that fits you well. I really don't know if this is a good time for you or not. But the lecture itself will be on Thursday at 1 o'clock. And I will let you know the lecture room a little later this week. And the lecture will be delivered by Professor Aaron Schwab, and it will be entitled as an Art of Bicycle Dynamics. So it's a little bit of special case about the dynamics, so you're going to learn about how is it you can make really something that is between art and science from bicycles. So, and now if you are unable to participate that in person, that will be fine, because lecture streaming will be available through my YouTube site, and also recording will be later available. So no worries. But there may be a question or two from that lecture in first midterm exam. So that's good to keep in your mind. Okay, so again, Thursday at 1 o'clock, Art of Bicycle Dynamics. And it is, if you want to familiarize yourself to this subject matter, you may log into Aaron's website, which is this one here. So there's a lot of stuff about bicycle dynamics. Bicycles, two wheels, vehicles, different kind of studies. And it is a really high-end studies. So he is a consultant of the Sunweb, which is, I believe, that is Tour de France team, one of the professional cycling teams, and is way beyond of that. There's a lot of stuff that is all related to bicycle dynamics, one way or another. And just one more marketing note. And not long ago, he published an article about the bicycle dynamics in Science journal, which is a really high-end journal. So consider to participate, and if not able to do so, then check it out the recording a little later. Okay, so with that, all the practical matters, is it more or less clear for you? So a summary today is recruiting day. Please try to participate. And then the midterm exam, you need to do the registration using this web body. And the next week, there will be, instead of one lecture, there will be two lectures. First one here on a Monday, and second one on Thursday. Clear? Okay, so then, last week we stepped into the world of flexible multibody dynamics. And we concluded that the flexible multibody dynamics can be categorized to two different fields, depending on the magnitude of deformation. And this is all about how is your strain displacement relationship. Is it going to be a linear or non-linear? Now, if your strain displacement relationship is linear, then you can only deal with the relatively small deformations. Meaning that if you have a cantilever structure and you're loading the free end of the cantilever structure, the loading end of the cantilever structure will remain in a loading line, which is completely fine if you deal with the small deformation. But you do understand that if the deformation becomes really large, this is very much against reality. And more realistic performance you can get by using a non-linear strain displacement relationship. And now the minor difference between this scenario and this scenario is the fact that here there's a little bit of deformation in axial direction, in longitudinal direction. And that's only possible by using nonlinear strain displacement relationship. Now here comes another important piece of information. This is, in practical applications, this is the most commonly used assumption. I mean, linear strain displacement relationship. And it is commonly used because it allows you to use modal reduction technique. It's a technique that you don't know yet, but you will learn later today. Why that is good? It is good because it can give you a method that is computationally very efficient. It can help you to avoid with the numerical stiffness, and it makes things to be efficient to compute. Here, modal reduction in general cases cannot be used, and that's why it is going to be computationally very demanding. So that's the difference between these two categories. Okay, so then last week we shortly looked at the, how is a lamp mass approach. And the lamp mass approach is a method that is, strictly speaking, not within the family of flexible multibody dynamics. And why is that? That's simply because theory, kinematics itself, is with no changes with respect to rigid and flexible bodies. This method takes the original body, which usually have to be the beam-like body like this, and divide that to number of rigid bodies. And between the rigid bodies, there are spring elements. So that's why there is no changes in the kinematics. You're just adding more components, bodies this time, and external applied forces. So that's all you need. Floating frame reference formulation that we really gonna take a look at in this class, and you really need to learn where the floating name is coming from. We are changing the kinematics. So this is a kinematics that is using a floating frame reference formulation. And there is a big difference, seemingly small difference, because vector U bar now consists of two components. The one that shows where the particle is originally located at, and then another component which shows how is the deformation of the particle. Seemingly just a little bit of tuning, adding more one component, but it changes everything, absolutely everything. And that's what we're gonna look in this class. And now, what we're gonna do then is that we're gonna describe this deformation by using a finite element method. Okay, now, we already learned a little bit about how is a finite element method. And in shortly speaking, finite element method is all about how is the internal life of one element. Last week we looked at the one simple spring kind of element, like element which is having two nodes. Excuse me, my drawing. So one node here, another one node here. And these nodes were able to move back and forth along the global x-axis direction. So it's kind of like element like this. So these nodes can move back and forth, and this is an element that consists of a total of 2 degrees of freedom. Where these 2 degrees of freedom are coming from, one node here, this node here can move left or right, so it's a 1 decrease. This node here can move left or right, so that's another decrease. Now, if I would add one more node in the middle, this would be then an element that consists of a total of 4 degrees of freedom. Correct. 3, exactly. 3 degrees of freedom, 3 degrees of freedom. I was just checking if you're still alive. 3 degrees of freedom. And where they are coming from, this one can move back and forth here, this can move back and forth, this can move back and forth. That's it. Now we know the number of degrees of freedom. What we will do next is that we will approximate the internal life, like the soul of this element, by using polynomial expansion. And polynomial expansion in this case is selected such the way that I have a constant value, which is a0, and then the value that is linearly related to x. So it's a1 multiplied by x. This is my polynomial expansion. And this is really the soul of the finite element method. What I could do is that I could use this polynomial as it is and solve the unknowns. And the unknowns this time are a0 and a1. Now that's the end of the story. Problem in these unknowns is the fact that there is no clear interpretation in real life. So if you get a1 and a0, what that means in real life, what kind of deformation it means. Well, of course, we can think about it, but there is no clear physical interpretation of what it is. So that's why it makes sense to convert these unknowns to be expressed by nodal degrees of freedom. And that's exactly what we did last week. And once we did that, then we get something that is a shape function. And it's telling you how the deformation, internal deformation of the element takes place. That's it. That's in a nutshell of the finite element method. Now, here, how is safe functions when using this polynomial expansion? With these safe functions, you can describe the stiffness and inertia, whatever you want. That's the finite element method in a nutshell. Okay. Now, where these polynomials are selected, how can I do the selection? Well, of course, it depends on what kind of element you're looking at. But typically, they are selected from something that is called Pascal's triangle. Pascal's triangle is the one that is shown in this slide. Now, last slide, I say that hypothetically, I could have an element that consists of 3 nodes. Each one of the nodes can move left and right, meaning that each one of the nodes have 1 degree of freedom. So now, if I'll go back to this Pascal's triangle and selecting my polynomials, how can I do the selection? I could get started, here. And now I'm looking at the 1 dimension only. So I'm looking at the element that is having just 1 dimension. So I could start traveling to this direction. How far I should go in order to be able to express the polynomial expansion for this element that consists of 3 degrees of freedom? Maybe you can say stop when I'm drawing the figure or this line. I'm starting here. Okay, so quite far off. So you say that I can go as far as I want. No limitation. That's not true. There's a limitation. So where should I? Let's try this again. So because I was kind of hearing that someone was saying stop and here. Okay, let's try again. So this is where I'm starting. So can I go here? Yes. Can I go here? Can I go here? Yes. Okay, I cannot. So here's how far I can travel. Why is that? So I need to stop there. Why is that? Because I'm simply looking at the number of components in my polynomials. And the number of components have to match with the number of degrees of freedom. Again, I have here 3 degrees of freedom. So that's why I can take 3 steps here. My first step, second, and third. Now, here comes really something surprising that I need to explain a little later to you. I can actually make these steps a little bit of unusual way, because I can actually do following. I can make my first 2 steps like shown here. Let me take these off as well. So I can select this one, I can select this one, and then I can select this one. And this will have a significant effect to finite element method. How it will affect, we will get back to that a little later. But only what matters, the only limitation we have is that we have to have 3 components. We have some additional limitation too, but this time let's just say that we can select 3 components. All right. So what about say what could be the something that is simple enough? Let's say that we have a beam element like this. And the beam element, I'm just describing that in a y direction, this direction, y direction. And this can move this direction, and it can rotate. So it consists of 3 degrees of freedom. Again, because here I have displacement here, rotation here, rotation here. So that's a total of 4 degrees of freedom. So how can I select my polynomials? I can select it such the way that I take this one, I take this one, I take this one, and this one. 4 components. So that's how it goes. The selection of polynomials is very essential in a finite element method. And why? Because it's predicting how the particles are moving inside of the element. And that's what is an essence of the finite element method. Okay, here's a question to you. Now, I have a spring element, and I'm having 4 nodes, and I'm asking what kind of polynomial expansion I can use to create the safe function. Only one is correct. Let me put the Socrative on. Oh, the Socrative is, okay, so hopefully this works fine. What? Is it that I don't have the internet access? No, I should have an internet access. Because I'm streaming all the time, so it should not be a big issue. Huh. What's going on? It works fine. Okay. This one. Okay, so you all, I can see that you're pretty much all in. Oh yeah, but this makes no sense to look at that. So let's look something else. Let's look this one. So I have 4 node spring element, meaning that the elements can move only left and right. So what is a polynomial expansion for this problem? You already know what's the correct answer? Should I take a look, like, how is my Socrative here? Okay, so like half done, half is still thinking. This is not that simple, isn't it? Semi-simple, let's put it this way. Why this is confusing, I will tell you in a minute. Okay, so another check to Socrative. Okay, so 6 students are still thinking. Can I go, or you want to have some time to think about this? Okay, so let me see. Okay, so the 4 students are thinking, but others are done. You guys done? Okay, what makes this confusing? C and B, because it's kind of it's tempting you to select B and C. Both are incorrect. There is I don't know, sometimes I think that this is like hilarious, or it's funny, but I understand that it's not funny. Only one that is correct is, hold on, here is D. Why did it is D? Okay, so let's take a look. By the way, it was good result, really good result. Kind of encouraging, but not 100%, of course. Why this one is only one that is correct? Because we are looking at the numbers, not the polynomial orders, but the numbers only. And now here I have 1, 2, 3, 4 degrees of freedom. So my polynomial expansion must have 4 components, because I have 4 unknowns. Now, this is not good because it consists of 2 unknowns. I cannot select that. This one is no good because it consists of, again, 3 unknowns. This consists of 3 unknowns as well. I know that this what makes you confused, but you should not get confused about that. This is the only one that consists of that number of unknowns. Okay, so let's move on. Let's look at something else. Now, here is a beam element, and this beam element is exactly like I explained in a previous slide. So this is the one that consists of 4 degrees of freedom. So 4 degrees of freedom, and these 4 degrees of freedom are translation along the global y-axis direction. And that in this node, and the same in this node. And then the rotation in first node and the second node. So you already know what's the polynomial expansion for this kind of element. So it's a polynomial expansion that consists of 4 components. Correct. Now what I will do with this polynomial expansion, I will go and change my polynomial coefficients to be expressed by nodal degrees of freedom. That will give me shape functions. And the shape functions telling me how the particles are moving with respect to each other in different kind of scenarios. And these scenarios are all related to nodal degrees of freedom. That's it. Now, then this will be later used mechanically to derive the stiffness and mass matrix, whatever you want. But that's mechanical, very mechanical. Only thinking you need to do is that when you select the polynomials and understanding how the polynomials will affect the shape functions. All right, so now here is an element where I'm assuming this motion in a y direction and angle to be related via this kind of a partial differentiation. This is a common assumption if you're dealing with an element that is not able to describe transverse shear deformation. We are not going to move deeper to that direction, but strictly speaking, elements can be divided to conventional elements like Bernoulli beam element that cannot describe transverse shear deformation, and then Timoshenko beam elements that can capture transverse shear deformation. But let's just leave it in that level this time. Okay, now a bit confusing is that I'm going to select my x coordinates, the one that I'm describing my motion in this y direction. I, of course, realized later that I should use these y coordinates. Again, I can select 4 components, and I'm going to select them like shown here. Okay, that's it. Now, here is something that I need to get back to this a little later. You need to remind me to get back to this. Yeah, so we still have plenty of time, so no worries. No worries. Okay, so now what I will do then, the same that I did in the previous case. So I will have my polynomial expansion as it is shown here. This is my original polynomial expansion. I'm going to express that with 2 vectors. One that is including my unknown polynomial coefficients, and then just the polynomials. Okay? Now my target here is to replace this one with nodal displacement, nodal degrees of freedom. Okay? So let's make it happen. So I can make it happen by using the information about where these nodes are located at. So first node is located in a place where x is equal to 0. Now x is measuring this direction, so it's going to be giving me this equation. The next one is a equation differentiated with respect to x, and then x again is 0. And then this one here is when x is equal to L, and the same thing here when x is equal to L. Now, here is my nodal degrees of freedom and my polynomial coefficients. This is a matrix that I need to invert in order to find relation between these 2 items. And remember this famous thing about matrix that consists of 48 times 48 components. That's what I was doing. Now it's already becoming more harder because this is 4 times 4. But it's nowhere near the nightmare that you're facing when it is this much. Still every now and then I woke up middle of the night and I can see these numbers in my dreams. So they are devil's number. Okay, so now here's my A. So I will just go and substitute that to this equation. It gives me shape functions. Now, this is how the shape functions looks in this beam element case. And now comes something that is very important. Now, these shape functions are orthogonal in a sense that if I look in the first shape functions, which is written here, this is the one that is associated to displacement, y displacement in my first nodal decrease of freedom. It is not introducing the displacement to any other nodal decrease of freedom. And that's something that is very important. Because if you look carefully at this shape function, here the angle is equal to 0. Displacement here, which is second node where that is located, is equal to 0, and the angle is equal to 0. How the particles are moving if I'm introducing the displacement to this one particular deformation mode. They are behaving according to these shape functions. And this tells me the soul of the element. This is inherent, like how is the performance of the element. Then next, I'm introducing displacement to this rotational decrease of freedom. You can see the displacement here is 0, displacement here is 0, and rotation here is 0. And the particles are assumed to behave according to this behavior pattern. Behavior pattern. So this is a good word for that. So it's a pattern of behavior. The same for this other end, like this. Okay? This is where the other node is located. So this is my displacement in the y direction. This is rotation in the y direction. And that's how they behave. So I say that I can do the selection how I want. There are some limitations other that I just mentioned, but yes, let's try what happens if I select this one, this one, this one, and this one. How is it going to change the behavior pattern of the element? Let's take a look at that. So here is my polynomial expansion. Excuse me, I select those incorrectly. So this is my polynomial expansion, so I need to go back here. So my selection was not the one that I saw it here, but it was this one, this one, this one, and this one. Okay, so let's see. Is it going to be any different? Yes, it will be different. It will be different. Now it's going to be a little hard to see how there is different, but if you go and compare the behavior pattern, in this case and the previous case, they look different. Which one is correct? This is, by the way, awesomely difficult question. Now, give a shot. Let's make because I can promise you this. If you can answer this correctly, next Monday there's a lot of candies. Because I go on Tuesday and collect a lot of candies and bring it to you. Which is correct? You said first one. Others? You say both? Come on, both. Is it possible? Because, in mathematics, it's only left or right, but not both. Can you select both? Yes, you can. Both. Candies. So it's a candy party. Nice. So both is correct. They're different, but they're correct. I'm not violating against any of the principles when I do this. They most probably behaves in a very different way. And how they behaves in a very different way, to be able to answer that question, we need to look at something that is called convergence. Element method is an approximate method, and it produces better and better solution when you're increasing the number of elements. And typically, displacement-based elements are approaching the correct solution from the stiff side. But if I'm selecting these polynomials like I did in this case, third order and fifth order is not guaranteed that is approaching the correct solution from the stiff side. It could actually approach the solution from other side as well. Because, let me see if this becomes clear enough. So let's say that I have here number of elements, and then I have here solution. And let's say that this is a correct solution, like this one here. Say correct solution. Typically you get very heavily stiff solution when you're using overly, just not enough elements. So let me change the color here. So you typically get the solution convergence that gets, get better and better like this. So it's able to produce better and better solution when the number of elements are increasing. This is typically how the element behaves if you're selecting these polynomials in the order that it is coming directly without making any skipping. Conformal elements, that's how they are called. But then there is a family of non-conformal elements that can approach the correct solution, for example, this way. They started here, but they're vibrating around the correct solution, and then they converge the right solution. It's possible too. The only way you can guarantee that they are converting from this side is by using conformal elements, meaning that the polynomials are selected in the proper order. Okay, but again, this is like I tried to explain here, the element method is all about internal life, about nodes. And this internal life is all about the polynomials. Polynomials are defining how the finite element method is performing. You knew this already, at least in a certain level. So you heard the story. How come you were able to select that both are correct then? I'm kind of sensing that there's a little bit of cheating from your side. No? Are you just that good? But no communication, no further communication. I understand that. All right. Okay. Now, let's go back to this, and then we're going to move. Now, to be able to make an element that is converging, it's not necessary that you can get an element that is converging, because if you select these polynomials randomly, then you can get really nice elements, but it's not converging the correct solution, which is a very big problem, a really significant problem. But this is, by the way, not yet guaranteed that it happens, but you must be able to fulfill these requirements to have minimum requirements to elements that is able to converge. The first one is the element have to be able to describe a rigid body motion without strain. This one here. Okay, now you should not mix this to rigid body motion and multibody dynamics. It means that if the element is in this configuration or this configuration with respect to global coordinate system, it should not give any strains. So if I have no deformation in this configuration or no deformation in this configuration, they should behave in the same way. How you can guarantee that? You can guarantee that by selecting polynomials from this Pascals triangle, such the way that the first component is this one here. This guarantees you that the element that can describe rigid body motion. So it's not the function of body displacement or orientation. Next is the element must be able to describe constant strain. That's because of the nature of the finite element method. Let's say that you have, let's make a simply supported beam like this. Not the best possible picture, but then this is loaded in a really complicated way. It's like there are forces back and forth like this. Again, quality is not the best, but what I try to say here, that in a case like this, strain distribution along the length of the structure will be, but better, more amplitude. Let me try to make it like something like that. That will be the strain distribution. Strain and stresses are related. Okay. Now, if I'm using one element or just a few elements to describe this kind of distribution, I will get really, really lousy solution. But once I keep on adding elements, really keep on adding the elements, then eventually, there within each one of the elements, I can approximate the strain roughly with the linear distribution. It's like steps-wise distribution. So here will be one. I need to apologize that this figure is so chaotic. But did you get anything that I'm about to explain here? So now, this is a requirement of convergency, that the element must be able to describe the constant strain. That one you can guarantee by select this component. This describes the constant strain. Then the final one really depends on your application, because it says here that displacement and their derivatives must be continuous enough to inter-element location. So meaning that, within the boundaries of the elements or within the neighboring elements, they cannot be gaps. And that really depends what kind of mathematics you need in order to describe the stiffness matrix and the inertia matrix. But let's look at the final requirements a little later. Now, if I'm selecting these polynomial orders as they are, then I end up to have a confirming element. And if I select them a bit more random way, I have non-confirming elements. That's how it goes. So, we were here. Now, in this case, this particular beam element, I'm describing my strain displacement relationship, first of all, such that my displacement and rotation angle are related using this equation, which simply meaning that I'm simply describing. Let me make a better drawing here. So I'm simply looking at the midline of the element. I'm looking at, for example, this line here. In order to compute this tangential here, I can do that with my partial operation like shown here, right? This gives me tangent of this middle line, right? Now, if I'm using the skew symmetric matrix, which you don't know how it is in planar case, but if I convert that with the 90 degrees, I will get something that is perpendicular with my tangent, right? And that I can do by adding the minus here. Let's just simplify it like that. And now, how much strain I'm introducing because of this bending is that, if I travel with this line more here as function of y is this direction here, I get more, and if I go this direction, I get more. This is the nature of the bending. So that's why this y is coming to this equation. Make sense? A little fast explanation, but let me repeat this fast. This is not really essential material of the course, but let me just repeat this fast. This is my midline of my beam element, all right? I wanted to see how the bending is associated to the strain in this direction, okay? So how can I make it happen? I make it happen in such a way that I will first compute the tangent of this midline. And then I flip 90 degrees this tangent, which I can do with the help of skew symmetric matrix. So that's where the minus is coming here. So I'm putting in this direction. So now this is perpendicular with respect to midline. So if I'm traveling more off from the midline, more strain I will get. Okay. So this is my displacement definition. And when I differentiate that with respect to x, this is a relation with my strain and displacement. Now, you can see that I need here second order differentiation. That's why the polynomial expansion in minimum have to be second order. That takes me back to this definition. Inter-element derivatives must be continuous enough. But it is guaranteed, so it's not a big deal. So that's how it works. Now I can get something that is very important. So I have here finally relation between my strains and nodal degrees of freedom. This relation, by the way, is actually expressed by kinematic matrix, which here is denoted as a B. Not really core information of this course, but just for your information. Kinematic matrix called B. Why this is kinematic matrix? Because it relates nodal degrees of freedom and internal strain. All right, that's what I need in order to compute the stiffness matrix, and I can get the stiffness matrix by simply taking the kinematic matrix and its transpose and multiply like shown here, and then I have my elastic coefficient, and that's it. That's going to give me the stiffness matrix like shown here. It's very, very mechanical, and you use a symbolic math tool, so it's very straightforward. Only thing that is not straightforward is selection of polynomials. Rest, mechanical. Okay. Now, this is where we're going to stop, because we need to discuss something very different than the finite element method. So this was a news flash, or introduction to finite element method. And this is a level of difficulty where when we're gonna leave the finite element method. No more difficult than that. Let me summarize this, because I want to keep on repeating. So finite element method is all about how you're assuming particles between the nodal locations are behaving. So it's all about that. This behavior can be predicted or can be described with help of polynomials. And it doesn't matter what kind of element you're looking at, it's always the same story. So if you're looking at the plate element, like this, 4 nodes, and these 4 nodes may have a rotational degrees of freedom as well. Same thing, it's all about the polynomials. Then, once you have the polynomials, then you're expressing polynomial coefficients with help of nodal degrees of freedom. What you're gonna get is a safe function. Safe functions gives you stiffness matrix once you have this kinematic matrix. That's it. That's a finite element method. I mean, that's the displacement-based finite element method. There are other types as well, but for sure we are not going to touch that. For sure we are not going to touch about shared deformable elements because they are painful. No, I say that it's possible that you can get the good performance when you have these, when you fulfill these 3 requirements, but not necessarily. There are still some problems that finite element method is suffering every now and then. And it is suffering something that you may have heard about, and it's called locking. So it's, again, not a mechanical lock, but it's a numerical lock. A numerical lock is something that is quite severe, and it can lead to a situation that prediction is very incorrect. Okay, so now remember this story about the 48 times 48, so that was a painful thing. There was another painful event that happened when I was a postdoc in Chicago. It was a shameful event. Can I share that with you? And it ended up to be a very happy event. This is a little bit of personal story, not in my side, but someone else in this department. So still I'm going to share this with you. Because, so I was there under this most famous professor in the field of computational dynamics. Well, at least really, really famous guy. And then the one student from Finland came to Chicago, and he got the task, simplest possible task. And the simplest possible task was to verify that this method that was using this high number of degrees of freedom is performing well. So really something that needs no particular skills. You just take the solution and you take a commercial finite element method, and then you compute the symbol examples with this new method and the commercial finite element software, and you compare how they are. And of course, the idea is to get exactly the same solution, right? Because everything went perfectly. And this student came, and then I still remember like yesterday, we had a meeting with this famous professor and the student from Finland. And then he got this assignment, and the professor was expecting that it takes, I don't know, a week, 2 max to do this accomplishment, or accomplish this. And then it took a month. Nothing really came out. And then finally the student called a meeting, and then he said that I cannot do it. And I was like, oh my God, this is so shameful, this is so shameful. He's coming from the same country than me, and now he's saying that I cannot do it. Please. Oh, this is really, really horrible, really horrible. And of course, the professor was upset as well. Like, what? You cannot do it. Like, I cannot really help you because this is the simplest possible task. I cannot give you any more simple than this. So can you just go and do it? And then the person, well, okay, let me try again. Another month. And then he called a meeting and said, I cannot do it. And it was like, oh, please, this is really, really embarrassing. This is cannot be even true. And then it was said that the visit was 3 months visit. So it was only 1 month left. So we set a lot of hope, like, please make it happen now, because otherwise this is very embarrassing for this person and very embarrassing to me, a little bit embarrassing to that famous professor as well. Well, final month, final meeting, and the person came and said, I cannot do it. That's maybe the lowest point in my career, so this is really embarrassing. The guy went back to Finland, and we were really happy because, no good guy, because he cannot do it. Then finally I arrived back to Finland, and I met this guy, and I say, I know the reason that I was unable to do it. The reason is locking. This new method that was developed is suffering from lockings. And he was able to prove that. Very solid way he was able to prove that. And he made a paper about this problem. And it's still one of my highest citing papers when you look at my publication. So this guy, he turned out to be really a success story. Why? Because he was not trusting professor. So this is a lesson you should learn. Professor can be wrong. You know what was the name of this guy? Jussi Sopan. He was that guy. Okay, now let's have a break, and then let's go to model reduction. Okay, so what is it, 5 minutes enough? Okay, 5 minutes.